Welcome back to multivariate calculus. In this video, we're going to be talking about iterated integrals. You learned in Calc 1 that the integral is, in a sense, the complement of the derivative. Not quite an inverse because there are infinitely many functions whose derivative lands at the same place, but interrelated in that same way. With the partial derivatives that we've been studying recently, there are several different ways that we can combine things. We can look at the gradient, we can look at the derivative in a couple of different aspects. And so because of that, there are actually three different ways that we can talk about an integral. Excuse me, there are three different ways we can talk about an integral for a function of several variables. The first one is the iterated integral. All right, without further ado, let me get my head out of the way and let's talk a little bit about what we mean by an integral of a function of several variables. Or more specifically, a trick that you are familiar with from Calc 1 or from Calc 2 is the area integral. If you are looking at a region in coordinate space, let's just take an arbitrary shape for now. If you have a definition as a function for the curve that makes up the top and the curve that makes up the bottom of your arbitrary shape, you can slice it into columns and calculate the area as the difference between the top and the bottom bit. That absolutely works. There's nothing wrong with approaching things that way. And in fact, in a lot of cases, it is the easiest way of dealing with it. But I want to look at things a little bit differently now. I want to go back to when you first started thinking about derivatives. You thought about these tiny little steps along the x-axis, and you called that tiny little step dx. And you added up all of those tiny little steps. Well, we can do the same thing in a two-dimensional region. We can take a tiny little spot here and call it some dA, some area differential. I generally will write my capital A to mean area, but I do want to mention that there are sources that will use lowercase a. So if you're reading on this elsewhere or it comes up in another class, you may see capital A, you may see lowercase a. There are a couple of other things that can show up as well, but those are far and away the two most common. But if I take my little tiny bit of area here, and if I'm going to be dealing with rectangular coordinates, where I have an x-axis and a y-axis, I'm going to assume that that tiny little bit of area is in the shape of a rectangle. So it has a length that I can call dx, and it has a height that I can call dy. And to calculate the area of a rectangle, you multiply length times width. dA is dy times dx. And so the total area of a region is going to be the integral, and we'll use a double integral sign to stress that this is a two-dimensional integral over the region we care about, of dA. And that's really all there is to it. All right. Well, I guess I know that dA is dy dx. The region that I am integrating over is something I don't know quite so much about. As I set it up before, I said that the lower limit on x was a, the upper limit on x was b, and I said that we knew the value of the curve up here. We called it f of x, and we had an expression for the curve down here. We called it g of x. And so this region is g of x less than y less than f of x, and a less than x less than b. And so here's where we get to the idea of iterated integral. I'm going to take my area here, my region, and I'm going to iterate it as two separate integrals. The integral x goes from a to b, and then the integral y goes from g of x to f of x. And I'll rewrite dA as dy dx. When you set up an iterated integral like this, it's important to pay attention to the order of your integration. What I want to think of here is that I have an integral. Y goes from g of x to f of x integrated with respect to y. And then once I've completed that integral, I will have another outer integral. X goes from a to b, integral of this thing dx. And so technically speaking, I don't actually need to write my y equals and my x equals because I have an integral right here. And if I didn't have y equals on my limits of integration, it would be very clear what it's supposed to be. And if I didn't have my x equals on the outer limits of integration, it would be very clear what it's supposed to be because it's the dx out here. So you will see in our textbook that they don't actually write that down. They just put integral from a to b, integral from g of x to f of x, dy dx, and they call it a day at that. I have trouble doing that because I make mistakes. As we'll see as we go through this process, trying to learn how to evaluate iterated integrals, changing the order in which integrals are evaluated is often going to be a very useful trick in figuring out ways of dealing with integrals that we couldn't otherwise. And so sometimes it's not immediately clear, or it's really easy to make a mistake and forget which order you're supposed to be writing things in, and then write your dy dx or dx dy backwards. So it's just a fail-safe that I have found is very useful, including for myself, putting in that extra x equals y equals. It saves me from making a number of mistakes. But look at what happens when you evaluate this integral. The integral of dy is y. So we'll evaluate y at our limits of integration. And we'll get f of x minus g of x dx, which was a very long way to go to get exactly the setup that we used in Calc 1 and Calc 2 to calculate the area of a region. So it's nice to know that it doesn't change anything, and it doesn't even actually change our process to have this new area integral that we can talk about. Before I move on and show why having this new tool can actually be useful, I want to mention here that this step, going from the area integral to the iterated integral, is called Fubini's theorem. I hope that in the discussion that we've just had, it's clear that this is something that we can do, and it makes sense in how we describe integrals that it works. But it's not the definition of an area integral. It has to come out of the geometry of the situation. And so it is a named theorem. It's named after a mathematician named Fubini, and I would be remiss to not mention his name as we go through this process. Now, with that idea in mind, let's go onward to things that we couldn't do with the rules for finding the area of a region on the plane that we've had before. In Calc 1, you learned about the integral as calculating the area underneath a curve. Extending that from a picture of x and y to a picture of x, y, and z. I apologize, this is going to be a terrible picture, as it always is when I try to draw things in 3 dimensions, but it will mostly get the point across. All right, but if we have a surface z equals f of x and y, and we have some region in the xy plane that forms the base of this 3-dimensional shape. I've drawn it to kind of look like a cylinder of finite height, but we can do the same thing. The area of a prism, so a cylinder like this, is the area of the base multiplied by the height. The height changes at every step in the cylinder, right? Volume in general is the area of the base times the height. And because the height changes in every single spot of this area, instead of just getting this in one step, we have to get it as a whole bunch of stuff added together. So we set it up as the double integral over our region in the xy plane as our height, f of x and y, times that little bit of area dA. And then we can use Fubini's theorem to rewrite this as an iterated integral. We'll start off with a couple of very simple regions of integration. Consider the function f of x and y equals y squared minus x squared. This is a hyperbolic paraboloid. And let's consider the region of integration. Y is between 4 and 6, x is between 0 and 3. Speaking generally, it is helpful to start off trying to graph the function in 3 dimensions is usually not useful, but graphing the region of integration will be useful. For these problems that we're looking at right now, not so much. But in general, looking at the region, figuring out what kind of shape you have and how best to describe the limits of integration can be incredibly useful. This particular problem, our shape is a rectangle. And so we can calculate the volume underneath this curve, or underneath this surface. It's the double integral over our region of f of x and y dA. Now we have our choice. We can either integrate y first, then x, or x first, then y. If our region of integration has some bias to it, sometimes one or the other of those is easier. This region does not have any bias to it whatsoever. So y then x is kind of the default if you don't have anything better to do. So our limits on x are from 0 to 3. Our limits on y are from 4 to 6. Our function f of x and y was y squared minus x squared. And dA is dy dx. Integrating y squared minus x squared with respect to y. Just like when we deal with partial derivatives, when we're dealing with iterated integrals, y is our variable term. Y can change. And while we're integrating with respect to y, we treat all of the other variables, like the x that appears here, as constants. But again, we're just dealing with this inner integral. We're integrating with respect to y. So y is a variable, x is a constant. Integral of y squared is 1/3 y cubed. Integral of a constant is that constant times y. Then evaluate at our limits of integration. 1/3 times 6 cubed. Well, 6 cubed is 216. 216 divided by 3 is 72. And then we have 6 times x squared. And then evaluating at 4. 4 cubed is 64. 64 over 3 is, well, just 64 over 3. And then minus a minus is plus, and we'll have 4x squared. All right, just evaluating at the limits of integration the same way you've done definite integrals since Calc 1. Clean up. 72, I already said, was 216 over 3. 216 minus 64. Let's see, 21 minus 6 is 15. 6 minus 4 is 2. So I guess that's going to be 152 over 3. Then we have minus 6x plus 4x. All told, that's minus 2x squared. And you'll notice at this point that I've dropped labeling x equals on my limit of integration because there's only one integral left. At this point, we literally are down to the integrals that we did in Calc 1. There is nothing new going on here whatsoever, but we will integrate. Integral of a constant is that constant times x. Integral of x squared is 1/3 x cubed. We have that coefficient of 2 that hangs around. Evaluate at the limits of integration of 0 and 3. 152 over 3 times 3 is 152. 3 cubed is 27, 2/3 of 27. Well, 27 divided by 3 is 9. 9 times 2 is 18. And then the lower limit of integration, plug in x equals 0, you get back 0. And do the calculation. 152 minus 18 is 134. All right, it's integrals. Integrals are never pleasant. It's definite integrals, which means that they are going to be computationally messy at times. But it's really nothing new once you buckle down and realize what's happening. Once you get past the notation, once you get past that setup on the very first step. If I scroll up and I step a little bit out of my way here, right? This very first step, going from this line to that line, that's new. That's a little bit confusing when you have to think about things in several dimensions. And that's why drawing the picture can be so very valuable, although these first couple of examples are not too bad. Once we have that picture, we can use that to set up our limits of integration. We replace dA with dy dx. We have an integral on the inside. We evaluate this integral the same way you learn to evaluate definite integrals in Calc 1. Once we've done that, we're left with another integral. We evaluate this integral the same way you learned how to deal with evaluating integrals in Calc 1. So as long as you are comfortable with that, the process is not too bad. If you're a little bit uncomfortable with dealing with integrals, it's been a while since we've really done any integrals, go back, review some things from previous mathematics courses. Other than that, it's not too bad. So let me get my head out of the way and let's look at one more for you to try. All right, so here we're looking at a function f of x and y is equal to xy minus 3xy squared. Region of integration is defined as the set of xy's where 0 is less than or equal to x is less than or equal to 2, and 1 is less than or equal to y is less than or equal to 2. I would like you to evaluate this function on this region. Again, if you like the physical interpretation, this is looking for the volume of the three-dimensional object, which is bounded by this region in the xy plane, bounded below by the xy plane, and bounded above by the surface z equals f of x and y. So calculate that volume, calculate that area integral, however you want to phrase it. See what you can do with this one. I'll see you in the next video.